Okay, next common example of a related rate problem, very common in almost every textbook, calculus textbook printed, is this problem of a sand falling off a conveyor belt forming a cone-shaped pile. And they give us a rate of 10 cubic feet per minute. They tell us the diameter of the base of the pile is roughly 3 times the altitude or the height of the pile. At what rate is the height of the pile changing when the pile is 15 feet high? So let's start with the equation for the volume of a cone. We'll insert an equation here, bump our size up first. New equation, the volume of a cone is equal to 1/3 pi radius of the cone squared times the height of the cone. Next thing we want to do is take a look at the information they give us in the problem. They tell us that sand is falling at a rate of 10 cubic feet per minute. So we're going to want to label that. And that is a rate of change. Cubic feet tells us that is a rate of change of volume. Per minute tells us we're changing as time changes. We've got 10. Let's make that a fraction as well. Well, we'll leave it out. 10 feet cubed per minute. Next important piece of information they tell us is that the diameter is equal to roughly 3 times the height. That's good information. It's not great information for us because we don't have diameter here in our equation, but we do know an equivalence for diameter. We know that diameter is 2 radiuses is equal to 3 heights. And that's going to become an important piece of information for us. If we look at this volume equation, when it comes time to take the derivative of this equation, keep in mind, r squared times h is a multiplication of 2 variables. When we're multiplying 2 variables, we would need to do a product rule for this. However, because we have this equivalence given to us, 2 radius equals 3 heights, we will be able to solve this for either variable and eliminate one of those. So let's move on to what other information are we given here. We're given the fact that we will have a height of 15 feet, and it is important, abbreviate that, to note that that is a changing dimension. So we're not going to be able to plug that in right away. That'll have to be at the end. And the last thing I want to note here is, what are we being asked to find here? At what rate is the height of the pile changing? Is telling me that we are looking to solve for dH dt. dH dt is what we're looking to find. Okay. Move down. So let's start by taking the derivative. Well, let's start by doing a substitution here. We know that 2r is equal to 3h. If we solve that equation, we're looking for dH dt. That means h has to stay in our problem. R is what we want to try and get rid of. So let's try and solve this equivalence. 2r equals 3h for r. And that's a pretty simple thing to do. We're just going to divide the 2 over to the other side. And we know that our radius is going to be equal to a fraction of 3 over 2 times height. Now that we know that, that's going to allow us to rewrite our volume equation as volume is equal to, I'm going to write this fraction as pi over 3. I'm going to put a parenthesis in, and we're going to get rid of radius and replace it with 3 over 2h. close the parenthesis, and remember, that radius value was squared. And this will all be times h. And if we simplify that even further, we'll now have volume is equal to, if we square 3/2, we get 9/4. And we get 9/4 times pi over 3. We can write that as 9 pi over 6, or we could cancel out a 3 and end up with 3 pi over 2. And I think that's the best way we want to write it. So we're going to have a fraction here of 3 pi over 2. We'll double check our math all the time. 3 squared is 9. 9 divided by 3 is 3. And that would be 4 in the denominator, because we squared that too. We'll have h squared when we square this, but h squared times another h, that's going to give us h cubed. And that's going to give us the volume equation that we're going to want to take the derivative of. And remember, we're taking a time derivative, so anything that's not time is going to give us a rate of change. So let's take that derivative. The derivative of volume is going to give us dv over dt equal to, follow your power rule, 3 times 3/4 is going to give us 9/4, 9 pi over 4. H is now going to be h squared times a rate of change of dH over dt. Excuse me. And now if we take a look at this, we have a dv dt was given to us to plug in. We have a value of h, 15 feet, that we can now plug in. And dH dt is what we're looking to solve. So we're going to go ahead now and plug all that information in. 10 feet cubed. Let's make this a little cleaner. Do a fraction here. Feet cubed per minute equals, need another fraction here, 9 pi over 4 times, we plug in our 15, so we're going to have 15 feet, and that's going to be squared, and that's multiplied by our unknown fraction that we're looking for, dH over dt. So we can go ahead and do our arithmetic here. 15 squared, of course, is 225. 225 times 9 is going to give us 2,025 pi. Equation 10 feet cubed per minute equals 2,000 fraction 2,025 pi over 4 dH dt. Now this unit here, because we squared this feet, is going to be feet squared. And that's going to be multiplied by our dH dt. Now we're going to take to solving this, and we'll simply multiply both sides by 4, which will give us 40. And then we're going to divide the 2,000 and what should be 25 pi underneath the other side. Should give us 40. Again, let's get back to the fractions and get this right. Make it look as neat as possible. 40. And we'll put our feet cubed there. our denominator is going to be 2025 pi. Remember that we had a unit of feet squared that we're going to divide over there as well. So in this denominator here, we're going to have feet squared, and we've got minutes down there. And why that's important is because we want to make sure that our units work out. That's going to be equal to our fraction now of dH over dt. So when we divided the feet squared over to the other side, we now have feet cubed divided by feet squared. Our units cancel just like variable exponents would. That's going to leave us with, maybe I should just move this down. Start over. Fraction 40 over 2025 pi, and that will reduce when we're done here. Our units have canceled. We now have feet per minute equals dH dt. And if we're going to reduce this, they're both obviously going to divide by 5. That's going to leave us with 8 over 405, and I think that's as far as it's going to reduce. So we'll put that in as a fraction. We'll leave it as a fraction. Fractions are always better than decimals, unless, of course, it's going to divide out perfectly and leave you with a terminating decimal. Nothing wrong. Because we have that pi in the denominator, we might as well leave it as a fractional form. Units, feet per minute equals dH dt. And that's going to be our final answer. So the important things when you do a problem like this, when you have these two variables here, r squared and h, is this step right here where I identified what we're looking to solve for becomes very important. Most times you're going to have some sort of equivalence, diameter to 3 heights, something like that you can eliminate one of your variables, and it becomes important to make sure you eliminate the correct one. The easiest one to eliminate would be h because it doesn't have the square, but if we do that, we're left with r squared, r cubed in the problem, and it's not what we're looking to solve in the end. There are other ways around it. You could certainly take the derivative of this equation, 2r equals 3h, and say 2 dr dt equals 3 dH dt, and then you'd be able to solve that equivalence and plug in for your dr dt's or dH dt's either way. That certainly could work, but I think that's an extra step. And I always have followed the rule that if you can simplify your equation before taking a derivative, you are finding the path of least resistance. So when you're given that extra equivalence, take the time, identify what you're solving for, make sure you keep that variable in the problem, simplify your equation as best you can, and then take the easiest derivative possible. In this case, it's really not that difficult of a problem. It looks a little confusing here. Maybe I'll space this out a little bit so that when people look at it, they don't get these equations all running into each other. But thanks for listening. I hope this was helpful, and I'll put another one together on another example later tonight or early tomorrow morning. Thanks a lot, and have a good day.